This is Paris podcast number 70, and today we're looking at the aerodynamics of a parachute. So we're looking at the aerodynamics of a parachute plus the hole on the top. So, the quintessential army parachute that you see in all the movies where it's very circular, it's just effectively just a half dome. That's the type of parachute we're looking at. And often in those movies, you see the hole on the top. So it's in a movie, so it's got to be true. And in fact, it actually is. So that theory makes sense. Some parachutes do have the hole on the top, particularly those circular ones. So to do that, we're going to be looking at a paper called a numerical and experimental study of the aerodynamics and stability of a horizontal parachute. And this is open access. You can find it in the link in the description if you want to play along at home. So let's get started. First of all, let's just cover quickly what they're going to look at. They're going to look at the effect of the Reynolds number, so the speed at which the parachute is going on the drag, and also the effect of that hole size, so going from no hole to having quite a large hole, how that affects the drag at different Reynolds numbers as well, at different speeds. So let's get into it. A parachute is generally equipped with a vent hole at the apex to allow some air to flow through the open canopy. As I said, movies are always correct. The canopy can be represented by a hemispherical shell, which has been shown schematically in figure 1. So let's go down to figure 1. So it's effectively just a half dome with a hole in the top, and it's dragged horizontally. Now, I don't know if the horizontal direction makes too much of a difference. I mean, gravitational effects will be different. However, considering that everything here is very light, and the inertia is very low, I don't think the gravitational effects will make much of a difference whether you're going down or across. As long as you're a sufficient distance away from the ground effect shouldn't be negligible. So I think it doesn't really make too much of a difference in this particular case whether it's horizontal or vertical. So the canopy is considered solid, and its direction of motion is from left to right, i.e. the flow direction is in the positive x direction. The flow structure near the wake of the canopy is responsible for the aerodynamic forces and moments it experiences. So obviously, a parachute is not potentially very well behaved aerodynamics around it. You could have some flow separation and some more common streets and this and that, which we'll get into. We'll look at the wake a little bit later. So the relationship between the Reynolds number and the flow field structure around spherical bodies in incompressible flow regimes have been studied extensively. Every Tom, Dick, and Harry has done it. The numerical study carried out by Natarajan and Akrivos indicated that the wake of a sphere becomes unstable at a Reynolds number of 100,000. So in other words, I'm guessing that you start forming quite a strong von Karman street. So the experiment, and actually probably a three-dimensional street of that. So the experimental results of a couple of other geysers showed that the hairpin-shaped vortices begin to periodically shed when the Reynolds number reaches 350. So I should mention actually that first study was actually at a Reynolds number 105, not 10 to the power of 5. I misread that. So it's only 105. So that means that a wake over a sphere is fairly well behaved below a Reynolds number of 105. Now, I'm not sure how accurate that number is because I've seen Reynolds numbers at 90, for example. And in fact, I've actually done simulations and even experiments where the Reynolds number is like 80, and you still do get von Karman streets around those objects. So what we're missing here is the thermal intensity, which I've talked about at length in other podcasts. Just quoting the Reynolds number and not thermal intensity level is not a very thorough way of making your results repeatable, because the thermal intensity level does affect transition and it does affect flow physics. So just the Reynolds number of 105, that might have been because it has a very low thermal intensity level, the wind tunnel that they were, or the simulation that they were conducting, whereas the other ones that I was doing, maybe the thermal intensity level was a bit higher. So that may account for the discrepancy. So let's move on to this other study, these other two geysers. So they showed that the hairpin-shaped vortices begin to periodically shed when the Reynolds number reaches about 350. So now they're talking about how effectively vortices shed as we increase the Reynolds number. So these two geysers' research indicated that when the Reynolds number exceeds 6,000, the vortex sheet separates from the surface of the sphere and becomes completely turbulent. So that's very low for there to be complete turbulence. Often we're looking at much higher Reynolds numbers, like around at least 50,000 to usually the juicy range is around 200,000 and even 500,000 or 1 million. So 6,000 is very low. I don't know what's going on there. So some other researchers also found that as the Reynolds number increases from 22,000 to 350,000, the boundary layer separation point would move from about 82 degrees to 132 degrees. So that makes sense. If you get a sphere and you say that like the 90-degree angle is the perpendicular to the free stream velocity, so right up, 82 degrees is slightly ahead of 90 degrees, which means that the flow is separating a little bit very upstream, sorry. As you increase the Reynolds number, that moves to very downstream, so 132 degrees. That's almost halfway between 90 degrees and 180 degrees, so it's very far back. And that's with increasing Reynolds number, and that makes sense because if you have a higher Reynolds number, two things occur. First, the boundary layer itself will have a greater velocity near the wall because it has more energy there, and that means it can resist flow separation better. So the adverse pressure gradient that you get on the cylinder or the sphere as you go around the back can be withstood for a longer distance because the boundary layer has so much more energy. Second, because the Reynolds number is so much higher, there's a good chance that the boundary layer is now a turbulent boundary layer or at least transitional. So what that means is the boundary layer profile, in other words, the velocity distribution as you move away from the surface is much sharper. So that means, again, that the boundary layer near the surface, the flow near the surface, is much faster. And again, it can withstand flow separation much better. So there are two reasons why this makes sense and why the boundary layer separation point moves backwards as we increase the Reynolds number. So that's all good. So a circular disk can be regarded as a good representation of round parachutes since the separation line is fixed at the disk edge. So a bunch of researchers have studied the flow structure around the disk and identified three instability modes: an axisymmetric oscillation of the recirculation bubble at a low Struhl number, so Struhl number of 0.05, a low frequency mode at a Struhl number of about 0.14, and a high frequency mode at a Struhl number of 1.6. The main recirculation bubble extends to about 2.5 diameters downstream behind the disk. So let's talk about this a little bit. The Struhl number, for those of you who don't know, it's a non-dimensional number that gives us a good way of comparing the periodic shedding of a certain phenomenon. It is usually vortices that we look at, but it could be any phenomenon, I guess, with other objects. So let's say I have two different objects. One's a cylinder, one's a sphere, or one's, I don't know, a shoe or whatever. These objects will have different Struhl numbers, and we can compare them to see what the frequency shedding is. And this Struhl number is based on the frequency shedding of the vortices, so how often these vortices are shed, the length of the object, the characteristic length, and the velocity of the free stream flow. And what they're saying here is, at different Reynolds numbers, they're getting different different Struhl numbers, they're getting different flow physics, which makes sense. There's I talked about in some other podcasts something called like a lock-in frequency, which is when you start to get to a certain frequency shedding, it actually hits the resonance of the object, and then that's called lock-in. So that's one phenomenon that can occur when you change the velocity of your free stream flow. So it's not unusual for this to happen. So moving on, a complete understanding of the flow physics around a parachute is still one of the most scientifically challenging issues from both theoretical and experimental viewpoints. In this paper, experimental tests and numerical simulations are conducted to obtain the drag coefficient on a hemispherical sphere for different Reynolds numbers and different vent ratios. So how big the vent, that circular hole on the top is. The vent hole is located at the shell apex. The main purpose is to find the effects of the Reynolds number and vent diameter on the drag coefficient as well as on the flow field. So these findings, this is juicy, they say these findings may be useful in parachute designing and its applications. So let's talk about the experimental setup. So the experiments were conducted under the free flow conditions, i.e. in atmospheric pressure and temperature. That's just a quick note on this. That's not for experiments. That's not that repeatable because both of these properties and the humidity also change. So atmospheric pressure could mean anything. It could be anything from like 98,000 pascals to maybe 104,000 pascals. Most people assume it's 101.3 kilopascals to 101,300 pascals, but that's just an average. It fluctuates. Temperature likewise, obviously the temperature fluctuates. So this is not exact. But anyway, The test rig was mounted on a vehicle which moved with a speed of 8.3 meters per second to 33 meters per second. The inflated canopy setup mounted on the vehicle along with the supporting hardware is shown in figure 2. So let's jump to that. And the parachute was assembled horizontally. And they have this setup, which is not to scale apparently. And they just have a parachute which is connected to a dynamometer. And a dynamometer is there to, it's used mainly in automotive engineering, but it's there to measure things such as power and torque output. But if you rig it properly, I guess you could measure drag as well. It's effectively the same thing if you rig it properly. So that's what they're using it for. So the flow visualizations confirm that the wake of the support rods, so all the stuff that they connected the parachute to the rig with, their effects are negligible on the dynamics of the parachute canopy. So that's good. That's something that you should look into as well. So that's good that they covered that here. The vent ratio of the parachute is varied from 0% to 20% of the diameter of the overall parachute. So it's quite large. The Reynolds number for a parachute canopy is commonly based on the diameter of the parachute itself. In this research, the Reynolds number ranged from 85,000 to 360,000, and the dynamometer was used to record the force at every stage of the experiment. So let's look at figure 3, which displays 2 typical parachutes with a vent hole used in the experiments. So what they look like are effectively like kind of like a skull cap or something like that, like just a half dome out of fairly rigid material. And one has like almost like a pinhole, or not much bigger than that, maybe like a pencil-sized hole in it. The other one has like maybe the size of I don't know, about 1 inch in diameter. So then they talk about their numerical setup. So let's talk about this a little bit because they cover a few different points here. So let's go back up, sorry, where they start talking about it. So they use a standard K-epsilon turbulence model. For those of you who don't know, if you hear something like K-epsilon turbulence model, so the letter K and then the Greek letter epsilon, you can be pretty much be certain that you're looking at some form of RANS, whether that's RANS, URANS, or DES. What that means is they're using 2 equations in this particular case to model the boundary layer flow physics. So how much the turbulence is affecting the boundary layer and whether how turbulent the boundary layer is. So this is actually a very basic approach, K-epsilon. This was very popular in like 2000s and 2010s and even a little bit earlier. And it was hailed as a massive breakthrough because there wasn't anything better. But since about 2010 or even earlier, there have been a lot better ones formed, such as the SST, which is a 3-equation turbulence model. Then there's SST gamma theta, SST K omega, and etc. So those last 2 are 5-equation models. Why that is important is because generally speaking, you can say that as you increase the number of equations that you're using in CFD, the more accurate your results will be. And in this particular case, that is definitely true because the SST to begin with is much better than K epsilon. The reason why is because with K epsilon and K omega, which are 2 very common, or at least used to be very common ways of modeling turbulence, they start breaking down in different parts of the boundary layer and flow. The SST does a much better job of remaining true regardless of where you are in the boundary layer or flow. And then SST gamma theta or SST K omega are even better. And then there are other ones as well. I just wanted to cover that they're looking at the standard K epsilon turbulence model. And they justify it below by saying, it may be noted that the RNG K epsilon turbulence model and more advanced turbulence models, such as the Reynolds stress equations, were also investigated, but these models could not give good numerical results. That's a little surprising. I'm a bit surprised by this because usually, as I said, you should get better results with a more a higher fidelity approach, such as the RNG K epsilon and Reynolds stress equations. However, they don't go into any other approaches, so I'm not too sure. So that's good that they checked out different ones and they found that the K epsilon in this particular case was decent. So since the experiments were performed under the free flow conditions, the parachute would not have a significant effect on the temperature of the air. I found that really interesting because what they're saying then is under certain conditions, the parachute could have an effect on the temperature of the air. I mean, if you were to go like 5,000 meters per second, you would then start hitting hypersonic speeds, and then you would get changes in the temperature, but they're not going nearly as fast as that. And they were sort of concerned about the temperature effect. So I was quite surprised to learn that the parachute can affect the temperature of the air even at fairly low speeds. That's something to maybe look into in another podcast. So, in addition, since the minimum and maximum Mach numbers are equal, respectively to 0.033 and 0.137, the flow is considered incompressible. Another little nugget of information: with the Mach number, it's very easy to understand when the air will be incompressible or compressible. So technically, regardless of what velocity you're at, even if it's at like 0.001 Mach number, so like 1 centimeter per second, air is not really incompressible ever. However, because the amount that the air compresses, so the density changes, is almost nothing at this velocity, we just say, okay, it's incompressible. And up to a Mach number of 0.3, we say air is incompressible. And that's because the density of air changes so little that we have made this rule of thumb that everyone really follows. Now, the idea that a Mach number of 0.3 is a good cutoff point, I would argue against it being a good cutoff point. I think it should be lower. It should be like maybe 0.2 or so. The reason why is because at 0.3, the density of air actually changes by about 2%. It compresses. So if you're okay with like a 2% error in your result, then that's okay, but I wouldn't be. So I think a Mach number of 0.3 as the rule of thumb is probably a little bit too lenient, and it should be lower than that. So that's the boundary between what everyone talks about, incompressible versus compressible flows. And here, both of these Mach numbers are well below 0.3, so they're saying it's incompressible, which is fine. The density effects would be almost nothing, like well below 1%, probably like 0.05% perhaps. So it's almost nothing. So the vent diameter and the Reynolds number are varied in order to study the effects of the drag coefficient as well as the flow structure. So how these change. They did a grid independent study, which is good. This is just in CFD where you increase the number of cells in your mesh to see how the effects are on different parameters, including the forces, so the drag coefficient. And the reason why you do this is because as you typically increase the number of cells you have, the more accurate your results will be. And you want to get to the point where this plateaus off and this is no longer the case. And there is a certain point usually where more cells do not give a better result. And that's the point where you can tell that your CFD is now independent of your mesh because you've hit that plateau now and you pick that point as the point to go from for your CFD. Anything below that, you're actually getting errors from the CFD approach influencing the results that you want. So they did that and that's good. So let's move on to the results and the discussion. So the drag coefficient. In order to investigate the parachute performance under different flow conditions, 6 parachutes with various vent diameters from 0 to 4%, 8%, 12%, 16%, and 20% of the diameter of the parachute, each at different Reynolds numbers of 86,000, 140,000, 145,000, 171,000, 230,000, 300,000 about, and 360,000 are studied in both the experimental and numerical cases. Figure 6 shows the numerical and experimental drag coefficient, CD, variations as a function of the Reynolds number for the different vent ratios. So let's go down to that and see. So across all the different parachutes with different holes in there, we can see that as the Reynolds number increases, the drag coefficient reduces. And this makes sense because this is most likely due to a reduced wake or reduced pressure drag. And the reason why that is the case is, as we mentioned earlier, as you increase the Reynolds number, the boundary layer becomes more turbulent for one. Second, so that has more higher velocity near the surface. Second, just because it is a faster moving flow, the boundary layer has a faster velocity. And so that means it can withstand the adverse pressure gradient longer and it can stay attached longer, which means the wake will reduce in size. And regardless of the vent, this is always the case that increasing the Reynolds number reduces the drag coefficient of all parachutes. Another interesting thing to look at is how the different vent hole sizes affected the drag coefficient. And generally speaking, as you increase the vent hole size, the drag coefficient drops a little bit. It's not a huge amount, but it is a little bit. It's not nearly as sensitive to the vent hole as it is to the Reynolds number, it seems. We'll get into that more later on. So they say, we'll just cover that quickly again. It is clear that for all vent ratios tested, the drag coefficient decreases by increasing the Reynolds number. In addition, the drag coefficient seems to experience a relatively sharp decrease at lower Reynolds numbers, but it takes a smooth change as the Reynolds number increases. So that's what I was talking about earlier. If you have a very sharp drop when you're at low Reynolds numbers, that's because at lower Reynolds numbers, the flow is very susceptible to the effects of the increased velocity, because just a little bit of an increase in velocity is going to result in a lot more turbulence, relatively speaking. However, once you're already in a turbulent boundary layer, increasing the velocity even more is not going to make the boundary layer even that much more turbulent, because we're already in a turbulent boundary layer. So there's a point where it plateaus off, and that's comes up in their results. So that agrees nicely with theory. They say one can also observe that the value of this drag coefficient reaches a constant value, and the diagram finds an asymptote. Although the trend of all the diagrams is roughly the same, this tendency is more evident for the parachutes where there is no vent hole, and the vent holes are either 12% and 20%. Now, I'm not sure why they're so varied. Like, they had other vent hole sizes, 4%, 8%, and 16%. So that's either something to do with a different flow physics happening, or just potentially due to error. I'm not sure which one. Next, they looked at the experimental drag coefficient as it changes with the vent ratio for different Reynolds numbers. That's in figure 7. So let's go down there and have a look. That's really cool. So what we can see is, as you increase the vent hole size, as we were talking about, the drag coefficient drops a little bit. Overall, the drag coefficient drops by about maybe 10%, maybe 8%, I'd say, with increasing the diameter from 0 to 20%. So going from 0% to 1/5 of the diameter being the vent hole, the drag coefficient drops by about 10%. And we'll get into why that is later on. Let's cover what they were talking about here. So they say that the results show that the drag coefficient decreases with increasing. There we go. The results show that the drag coefficient decreases by increasing the Reynolds number. This is attributed to the fact that the formation of the wakes behind the parachute causes the drag force to decrease. In all the Reynolds numbers tested, except in the last two, so 300,000 and 360,000, the parachute with 4% of the diameter of the overall parachute diameter possesses the highest value of the drag coefficient as compared to the other vent ratios. So it's even worse than having no vent at all. So that's interesting. Why would that be? Probably because when you open the parachute a little bit, so there's a little pinhole in it, you now have air going through, and that's going to change how the wake forms behind it. So with no vent, there might have just been this stable flow and the wake would have been okay. But now you've introduced a little bit of, effectively like a jet into the wake, and that could change the roll-ups. We'll look at that a bit later as well. So according to this figure, the maximum amount of the drag coefficient achieved during the experiments is 1.77, which, by the way, we do want a high drag coefficient for parachutes. This is one of those topics where a high drag coefficient is very good. You don't want to have a low drag coefficient for a parachute, because then you'll fall through the air quicker. And they say for the drag, when the parachute opening is greater than 4% of the diameter, the drag coefficient will be below this maximum value for all of the Reynolds numbers tested. Therefore, at high Reynolds numbers, it is suggested to use parachutes without vents, since such parachutes experience higher drag coefficients in comparison with the other cases. So it's interesting that they have a higher drag coefficient with no vent. However, a lot of parachutes do have vents. So then maybe there's some sort of stability effect happening there. For all the vent ratios and the Reynolds numbers tested, 2 wakes both inside and outside the parachute are observed. The size of these wakes seem to increase moderately as the Reynolds numbers increase in size. Increases the Reynolds number. That is a bit counterintuitive, because you'd expect the wake to reduce because the flow is staying attached longer. They say in general, the vent ratio is the main cause of the pressure difference decrease across the wall of the parachutes, i.e. between the outer and inner regions of the parachute. In fact, by increasing the vent diameter and the outflow flux increases, hence decreasing the pressure difference between the inner and outer regions of the parachute. So this is explaining why we see a drop in drag coefficient as the vent size increases. What happens is you have a jet going through the rest of the wake, that results in the pressure on the outside of the parachute, so the top surface, increasing a little bit because now you don't have just a massive wake there. So if you have a higher pressure on the outside, that alleviates some of that pressure difference, and that means that you have a smaller force, and that means you have a lower drag coefficient. So that's how that works. So stability analysis. During the experimental tests, the parachute was observed to be oscillating when the Reynolds number exceeded some certain values. At low Reynolds numbers, so this is a fluid structures interaction where the aerodynamics is causing the structure to change in shape. At lower Reynolds numbers, the parachute was found to be stable without any oscillations. However, as the Reynolds numbers increase beyond a certain value, the parachute becomes unstable. So transitions from stable to unstable conditions were observed for all vent ratios. It is clear that as the vent diameter is increased, the transition from stable to unstable conditions is delayed. If for a parachute without a vent hole, at a Reynolds number of 85,000, no oscillations are observed. However, for a Reynolds number of 114,000, they observed very intense oscillations. For the parachute with a vent ratio of 4%, the oscillations were commenced at a Reynolds number of 114,000. It may be concluded, or may be noted that by increasing the vent ratio, the critical Reynolds number at which the parachute started to oscillate is increased. For parachute with vent ratios of 8% and 12%, the critical Reynolds numbers are 171,000 and 292,000 respectively. So let's go down to some figures. First of all, they have wakes for these different parachute openings and at different Reynolds numbers. First of all, as you increase the opening size, the wake becomes less wakey because you have a jet going through. So earlier they said that as you increase the vent diameter, the wake increases in size. That may just be due to the jet itself, like pushing the air out more. So even though the wake looks bigger, the volume that the wake takes up is actually smaller because much of that volume that you thought was the wake is actually a jet. And jets mean that you have a higher velocity. And that is usually coupled with beneficial things for reducing drag. In this case, you don't want to reduce drag, so that's bad. So that's how increasing the vent ratio affects the wake. Increasing the Reynolds number also increased the wake size. However, it's interesting because over the top of the canopy, it seems like there's a slightly faster moving flow for some reason as you increase the Reynolds number. So that would probably result in I think the flow is still attached more, even though the wake looks bigger. I reckon that the flow is attached a little more. That's what the wakes look like. So there's a strange flow physics going on. Also, there is periodic shedding of vortices. There's this recirculation, which I've found a lot in my simulations as well. So that makes sense. Now, let's move on to the stable and unstable zones obtained by the experimental analysis. Now, interestingly, as you mentioned earlier, as you increase the vent size of it, the Reynolds number you need to trigger instability increases. However, there's also a transitional point. And that's quite interesting where it covers quite a big range, about 100,000 Reynolds number range is where this transition region occurs. I don't think it has anything to do with the, I don't know. It's strange that it's very close to the transitional regime in terms of the Reynolds number, but I'm not sure how this vent hole affects the laminar to turbulent transition regime, that physics there. If you have any idea, actually, let me know in the comments below because I'm quite curious about this. This is one thing that we haven't covered in this podcast, how the vent ratio could affect the Reynolds number and the transition to laminar to turbulent transitions. So let's conclude this. They say the results show that for all cases, as the Reynolds number increases, the drag coefficient decreases. At higher Reynolds numbers, the parachute without vents experiences a higher drag force as compared with other cases. The parachute begins to oscillate when the Reynolds number exceeds a certain critical value, which is different for different vent ratios. This would imply that every case is a stable and unstable region. As the vent ratio increases, the oscillations would occur at higher Reynolds numbers, and that would have a feedback to the fluid structure interaction I mentioned earlier. So that's in this podcast. Make sure to like and subscribe, and check out the Atmosphere Hawk, which is an experimental instrument we make to accurately measure the density of air in your experiments. The reason why that is important is because the density of air changes by about 2 to 4% on a regular day, and then even more between weeks and seasons. And if you don't measure the density in your experiments, you have that error creeping in, and it means your results are going to fluctuate, and you're not going to be able to find trends nearly as easily. And the trends you do find potentially are not going to be actually true because you haven't taken account of the density. So Atmosphere Hawk gets rid of that error for you. It's very easy to use. Link in the description. Get one for yourself, makes your life easier. And I'll see you next podcast. Peace out, amigos.